Hi again, everyone. So, we're continuing on with nervous system, and we already started with myelination, nerve fibers, and conduction, and started looking at some of the pathologies. However, I wanted to let you know that this is the second part of the video, right? So this is part two, because I had to break this one up into two parts. Part two. All right. Okay, no more parts, just part one and part two. All right, let's go ahead and get started. So during myelination, the nucleus doesn't migrate around the axon like a Schwann cell, okay? Because it's kind of stuck between all of these different types of neurons that it's holding together. So what it's going to be doing is it's going to push layers of myelin under the old ones. So it's kind of an interesting thing. So it's spiraling in, constantly kind of turning in and in and in to produce its myelin. The other thing is it doesn't include a neural limbic component. So here we've got the dendrocyte, right? The oligodendrocyte. So remember dendrite, okay, arms and legs. Oh, well, there they are. Oh, there's some dendrites right here. All right. And as you can see, it's pushing, its arms and legs are reaching out, and they're the ones that are surrounding the nerve fibers, okay? Unmyelinated axons. Many neurons have unmyelinated axons. So what this means is if you have unmyelinated axons, you'd think like, oh, you know, there's nothing in the way. It's going to move super fast, right? Actually, that's not the case at all. It kind of does this thing where it starts off like a big signal, and then it gets quieter and quieter, and then the signal goes slow, right? Whereas if you have a neuron that is myelinated, right? And so here's some of her myelinated components, little Schwann cells. What ends up happening is every time you jump over these nodes of Ranvier, that signal is thusly re-amplified to be nice and big, exactly where we need it, right? So myelination actually causes it to be a little bit quicker. So in the peripheral nervous system, Schwann cells hold 1 to 12 unmyelinated axons in these little surface grooves. So this is kind of what it looks like, right? So right here is unmyelinated nerve fibers, as you can see. Okay, they're kind of embedded in there, right? And they're very small, so these axons are teeny, teeny, tiny, because you can see other components, like here's a mitochondria right here, and here's part of the ER over here, and of course here's like that nucleus itself of the Schwann cell. And then on the outside is that nice thick base layer, that basal lamina, right? It's like, I guess you kind of think of it as the nice thick sweater around it. So conduction velocity, meaning how fast are we conducting that signal? So it's the speed, again, of which the nerve signal travels down the axon. And it needs to look for two things. Number one, how thick is it? What is that diameter? Is it very small or is it a very large diameter? Remember, diameter is from side to side all the way across. Like, what is that distance? Okay. So larger axons are going to have more surface area, and they're going to conduct signal more rapidly, just because there's going to be more stuff there, more electric-like activity on that surface. Other things that matter, whether or not you have myelin, we already learned a little bit about that. And we know, again, that myelin, having it, speeds signal conduction, and it makes that communication signal go faster. Conduction velocity. So here's some speeds to think about. A small, teeny tiny unmyelinated fiber. So it's going to be generally your slowest one. So it's going to go 1.5 to 2 meters per second. So like maybe like 1.5 feet to like 6 feet a second. And that seems actually kind of fast when you think about the size of the human body. But these types are going to be used in places like, you ever notice that, I don't know about you, but I'll get really hungry and I'll go get this plate of spaghetti, and it won't be like a normal size plate. It'll be like the dinner plate, and then I'll melt all this cheese on top of it, right? The next thing that'll happen is I'll sit down and I'll devour it super fast. Maybe like, I don't know, too quick to embarrassingly say on a video. And then instead of waiting or drinking a glass of water, I kind of just want to go back and get another huge mountain of spaghetti. And then, you know, after that one, I feel a little more full. The problem is if that's taken a whole 20, 30 minutes for me to eat these two giant heaps of spaghetti, I'm going to feel way too full. But if I would have just eaten the one plate of spaghetti and waited that 20 minutes, I probably would have felt just as full. It's because those neurons that are in your guts are slow. They're actually working against you in terms of keeping all that spaghetti away, right? And the reason is because normally, since we're apes, like we're supposed to be eating salads and stuff, so those take a while. Me and spaghetti, that doesn't take a while. Medium ones are going to be small, what we call lightly myelinated fibers, right? So we have the lightness of the myelination. But then ones that you're using for, say, like super fast coordination, like maybe doing calculations in your head or playing basketball or doing ballet, those are going to be really fast. They're very large. They can have a huge jump in potentiation and they can go very far, very fast. So 120 meters per second is incredibly quick. Now that's that electric-like signaling in its finest. So these large axons are going to need large cell bodies because that's a lot of energy and a lot of chemicals in order to push. So faster conduction velocities are required for a few things like muscle control and coordination, right? Basketball and, ballet, all of that. And then slower conduction velocities are sufficient for things that we don't need quick responses, like me and spaghetti. Okay, everyone. So, wow, I think it's time for another cup of coffee. But thanks for sitting around with me again and going over some more neuro. And quite a few other videos coming up, so stay tuned. All right, well, have a wonderful day.